In the previous video, we dove deeper into atomic structure and the principles of bonding when we looked at periodic trends. In this video and the one to follow, we will be introducing electron configuration. At its heart, electron configuration is the examination of how electrons are distributed in an atom. We learned previously that electrons are negatively charged particles that orbit an atom's nucleus along fixed paths called orbitals. The attraction between the positively charged protons in the nucleus and the negatively charged electrons orbiting around the nucleus is what gives atoms their shape and structure. Electron configuration gives us a method by which we can denote the positions of electrons inside these orbitals. Essentially what we're doing here is zooming in on atomic orbitals and trying to figure out how electrons move inside these orbitals. The reason this matters is because as we move further into this series, chemical bonding and molecular structure will become two of our main areas of focus. In order to really understand how bonding works at the atomic level, we need to know just a little bit more about how electrons are involved in this whole process. Before we start an in-depth discussion of electron configuration, it has to be said that this is one of those topics that many students don't fully understand when they study it as part of a general chemistry course. This is because a comprehensive treatment of electron configuration is in the vein of quantum chemistry and atomic physics. And as we established earlier, those subjects are beyond the scope of a series intended for an audience that is most likely studying chemistry for the first time. In the end, we end up stuck in an awkward position. Either we don't talk about electron configuration at all, in which case we walk away with an incomplete and oversimplified understanding of how atomic structure works, or else we discuss quantum chemistry in detail and end up confusing ourselves. Most general chemistry courses try to take a middle path between these two extremes. They do talk about electron configuration, sometimes devoting an entire chapter of a textbook to it, but they don't get into too many details and avoid explaining everything thoroughly because it is quite literally impossible to explain every aspect of electron configuration without bringing in quantum chemistry and atomic physics. For the sake of viewers watching these videos to review for an exam, and those who are here for a review of their teachers' or professors' content, this series will follow the same route. More specifically, we will talk about electron configuration, but only with the goal of equipping ourselves to actually write the configurations for different elements. In other words, we will for the most part ignore the conceptual aspect of electron positioning and focus primarily on the practical details of how to write the electron configuration for any element put in front of us. Anyhow, that was just a brief explanation as to why electron configuration is part of this series. Let's begin today's discussion by defining electron configuration. As we've already stated, electron configuration is a way of showing how electrons are distributed in an atom's orbitals. There are three methods of showing electron configuration: the long-form notation, the shorthand or noble gas notation, and orbital diagrams. The plan here is to split our discussion of electron configuration into two videos to keep either installment from becoming too lengthy. Today, we will introduce the concept in long-form notation, as well as how electron configuration relates to the periodic table. In the next video, we will discuss the shorthand way of writing configurations in addition to orbital diagrams. Remember, electrons in an atom travel on orbital paths, and these orbitals can only hold a certain number of electrons. It's also important to keep in mind that, despite the common practice of drawing atoms as two-dimensional diagrams, they are in fact three-dimensional particles. The concept of dimensions is important to understand here. A piece of paper, or in our case a tablet, realistically can only show two dimensions at a time. Imagine a coordinate plane. We can draw a vertical line and label it the y-axis, and we can draw a horizontal line and label it the x-axis. Yes, diagonal lines are also possible, but moving diagonally is ultimately little more than moving in both the vertical and horizontal directions at the same time. There is no third dimension on a piece of paper unless we employ special drawing techniques for depicting things in 3 dimensions, the way an architect or engineer might while making a technical drawing. Real life, however, occurs in 3 dimensions, so we have to start thinking of atoms as 3-dimensional. Electron orbitals are therefore 3-dimensional rotations, and electron shells are further divided into one or more subshells, which in turn contain the actual electrons. So we have a threefold structure here. Electron shells, these are the circular paths that we've been drawing in our atomic diagrams, are the largest group. Electron subshells are one level down, and the lowest level are the electrons themselves. The first two levels, or shells and subshells, are our primary concern today. Most atoms encountered in a general chemistry course will have 4 orbital shells. They are called the K shell, the L shell, the M shell, and the N shell. It might be noticed that there are these numbers here that are set to equal the variable n. The variable n represents a parameter called the primary quantum number. The primary quantum number has 2 functions. The first is to denote the energy level of the orbital shell in question. Essentially, energy levels are a measure of how far away from the nucleus a particular orbital shell is. A lower quantum number corresponds to an orbital shell that is closer to the nucleus, whereas a higher quantum number corresponds to an orbital shell further away from the nucleus. From this, we can conclude that the K orbital shell is the closest to the nucleus and the N shell is the furthest away. Some textbooks will actually do away with these letters altogether and simply label the energy levels using their corresponding primary quantum numbers. If we look over here to the right, we'll notice that an atom can actually have up to 7 energy levels in total, and the elements with the highest atomic numbers do go up to 7 orbital shells. However, the first 4 shells are what most general chemistry textbooks and instructors tend to focus on the most. Even so, it should be kept in mind that 4 is not the maximum value of the primary quantum number. The second purpose of the primary quantum number is to tell us how many electrons each shell can hold. We can find out this value using a principle from quantum chemistry called Pauli's exclusion principle. The actual principle is too complicated to state word for word here, but what we can get from this axiom is the notion that a single orbital can hold 2 electrons. From this we get the formula 2 times n squared. Solving this formula using the primary quantum number for n yields the maximum number of electrons a shell can hold. Let's practice this with example 1, which says, state how many total electrons can be found in each orbital shell. Here we have the letters M, K, L, and N on the left, and over here on the right, we have to write down the maximum electrons each of these energy levels can hold. You may pause the video here if you'd like to try this problem yourself. First we have orbital shell M, which, if we scroll up a bit, we see has a primary quantum number of 3. If we use our formula, we find that shell M can hold a maximum of 18 electrons. Secondly, we have orbital shell K, which has a primary quantum number of 1. After doing the math, we see that this orbital shell or energy level can hold 2 electrons. What about orbital shell L? Its number is 2. So it can hold a total of 8 electrons. Finally, we come to orbital shell N, with a primary quantum number of 4. Using our formula, we find that orbital shell N can hold a maximum of 32 electrons. Now, we said earlier that orbital shells are the first major division of electrons. The second layer are the subshells, which each of the above orbital shells are divided into. There are 4 main types of subshells, and these are denoted with the lowercase letters s, p, d, and f. Subshells are differentiated based on both their azimuthal quantum number and their shape. The azimuthal quantum number isn't too crucial a concept at the moment, but what is important to remember is that it begins with 0. The S subshells correspond to an azimuthal quantum number of 0, the P subshells correspond to an azimuthal quantum number of 1, and so on. From a physical perspective, the shape these subshells take on is the primary differentiating factor between them. The S subshells have a roughly spherical shape, the P subshells look somewhat like a dumbbell, and the D and F subshells have more complex shapes that are difficult to describe accurately using words. Having introduced the concepts behind electron configuration, let's look at how to go about writing one. A basic electron configuration has the following notation. We will notice that there are 3 characters involved here, 2 numbers and 1 letter. The number on the left in front of the letter X represents the energy level of the subshell. Remember, the energy level number is the same value as the primary quantum number, so we're looking at a number between 1 and 7. The letter x will be replaced with either s, p, d, or f, depending on which subshell shape we're talking about. Finally, the numerical value of the exponent on the letter tells us how many electrons are to be found in the subshell. At the end of the day, a single term of an electron configuration is just a way of showing exactly how many electrons are found in a subshell, what type of subshell is involved, and the distance between that subshell and the nucleus as shown by the energy level. A full electron configuration, then, is made up of all the terms corresponding to all the subshells involved in a specific atom. Before we start looking at actual electron configurations and start practicing how to write them, we need to discuss another principle from quantum chemistry. This principle is called the Aufbau principle. The word Aufbau is a German language term that means building up, which makes it a perfect descriptor for the idea behind this principle. The Aufbau principle states that lower energy levels, once again, all we mean by this are the electrons found closest to the nucleus, get filled with electrons first. So the subshell 1s, which has an energy level of 1 and a subshell type of s, will be filled with electrons before the subshell named 2s. The best way to demonstrate this principle is to examine an actual electron configuration. So here we are. This is the full electron configuration for the chemical element oganesson, which has an atomic number of 118 and 118 total electrons. Normally, electron configurations are not color-coded. The purpose of writing the configuration in different colors is to show which of these subshells belong to which energy level. As we can see, the configuration begins with the orbital 1s, which, in any atom of oganesson, will have 2 electrons. The next orbital is 2s, which has its maximum of 2 electrons. The orbital 2p is holding its maximum electrons, a total of 6. On and on we go until we reach the final subshell, 7p, which has its maximum of 6 electrons. Also, the order these subshells are listed in does matter. The lower energy levels must come first according to the Aufbau principle. All this may look quite intimidating, but remember, an electron configuration is nothing more than the collection of an atom's subshells laid out. From a single glance at this configuration, we know that oganesson has 7 circles around its nucleus, and if we were to sit down and add together all the exponents, we would know that it has 118 electrons without ever having to look at a periodic table. Another reason we've chosen to look at oganesson's electron configuration is because this is the longest electron configuration a current student of chemistry will ever see. All the other elements have electron configurations shorter than oganesson's, so we can work our way backwards, so to say. A main reason why electron configuration can seem intimidating is because of the sheer number of letters and integers involved. Fortunately, there's an easier way of visualizing and remember the exact order of these subshells. I like to call this the snake diagram. I'm not quite sure if anyone else calls this the snake diagram, and there's certainly a more technical term for it out there somewhere, but it's a useful tool no matter what we call it. The idea here is to look at each one of these arrows as a snake. The arrowheads represent the heads of the snakes, and the ends without the arrows are their tails. It's never a good idea to touch a snake near its head, and we also don't want to tackle a pit viper before we know how to handle a garden snake. So we want to begin at the tail of the smallest snake, which is this arrow on the bottom of the diagram labeled with the number 1. If we move along the arrow from tail to head, we hit the subshell 1s, which can hold up to 2 electrons. The second snake also has swallowed only 1 subshell, which is 2s. The third snake contains subshells 2p and 3s, and so on and so forth. It's quite easy to follow the pattern here if we move horizontally down these rows of subshells. Each row has subshells with the same leading integer, a number between 1 and 7. The subshells always are written in the order of s first, then p, d, and lastly f. Even the maximum number of electrons, the value of the exponents, follows a pattern. This makes it a simple thing to draw one of these diagrams whenever we encounter an electron configuration problem. Speaking of electron configuration problems, let's try one now. I do recommend watching this problem as we work it out together, but if you'd like a challenge, feel free to pause the video, draw a snake diagram, and see if you can figure it out for yourself. Otherwise, let's begin. This is example 2. Example 2 would like us to write the electron configuration for oxygen. Now, our immediate plan of attack for these sorts of problems should be to turn at once to our periodic table and check the atomic number for the element involved. In this case, oxygen has an atomic number of 8, which tells us that oxygen has 8 electrons to balance out its 8 protons. Our second step should be to scroll up to our snake diagram. The first subshell is going to be 1s, and because of the Aufbau principle, the 1s subshell is going to be completely filled with 2 electrons, as denoted by the exponent. That's 2 electrons taken care of, so we can subtract that from our total of 8 to get 6 remaining. Snake number 2 gives us the 2s subshell, which is once again entirely filled with 2 electrons. Only 4 electrons left. Starting from the tail end of snake number 3, we get the 2p subshell. However, because we only have 4 electrons not yet accounted for, the exponent on the 2p is going to be 4 instead of 6. In other words, the 2p subshell of an oxygen atom isn't filled to capacity with electrons. And there we have it. The full electron configuration for oxygen, written in long-form notation. Example 3 now. Write the electron configuration for calcium, abbreviated Ca. This one you can try on your own if you'd like. Calcium has 20 electrons, as given by its atomic number. We can shortcut our way through this configuration by copying the configuration for oxygen. The reason we can do this is because oxygen has fewer electrons than calcium, so the first few subshells of calcium are going to be filled in exactly the same manner as those of an oxygen atom. We do, however, have to make one change, changing the exponent on 2p from 4 to 6, since that subshell is now full. Just like that, we've already accounted for 10 electrons, only another 10 to go. The next term is subshell 3s, filled with 2 electrons. Only 8 more to go. Snake 4 gives us 3p, filled with 6 electrons. The last 2 electrons are going to go in subshell 4s with the exponent 2. If we add up all our exponents, we will see that we've accounted for all 20 electrons, and we therefore have here the correct electron configuration for calcium. Our final topic for today is the relationship between electron configurations and the periodic table. We've already talked about periodic trends in some detail, but we haven't yet discussed the practice of dividing the periodic table's elements based on their electron configurations. This is done by dividing the table into 4 blocks: the S block, the F block, the D block, and the P block. It might be noticed that the letters denoting these blocks are the same as the lowercase letters used to denote subshell shapes, and this is done with good reason. The lowercase letter of a particular block tells us at a glance what subshell that element's valence electrons will be found in. The valence electrons of an atom whose element is in this S block, for example, will have its outermost electrons in an orbital of the S subshell type. The S block constitutes all the elements in groups 1 and 2 plus helium. Most of these elements are highly reactive, have low melting and boiling points, and are generally highly electronegative. The F block contains almost all the lanthanides and actinides, namely the elements between lanthanum and ytterbidium, and those between actinium and nobelium on the periodic table. The D block contains what are generally referred to as the transition metals, found in groups 3 through 12. Last but not least, we have the P block, the only block that contains metals, nonmetals, and metalloids. It is comprised of elements in groups 13 through 18, exclusive of helium. Here we have our old friend, the PubChem periodic table, this time showing the electron configuration blocks. The elements in red are part of the S block, those in blue are part of the F block, those in yellow are the D block, and those in green are the P block. Knowing which block a particular element is found in can be helpful when writing electron configurations. This is because an atom's valence electrons will always be found in the outermost energy level, which is denoted by the final or rightmost subshell in any configuration. We can verify that we've written the correct configuration by making sure the rightmost term corresponds with that element's periodic table block. If we go back to example 2 here, we will notice that the rightmost term of oxygen's electron configuration is 2p, which in this instance has an exponent of 4 instead of 6 because the subshell is not filled to capacity. We'll want to remember the 2p subshell because if we scroll back down to our periodic table, give me one moment here, we will see that oxygen is colored in green. And green is a color of elements in the p block. Because the letter of the block and the letter of the rightmost subshell match, we know that we've stopped the configuration at the right term. For those who are curious, it is true that oxygen has 6 valence electrons in total, so it might seem odd that 4 of these electrons are in the 2p subshell, while the other 2 are in the 2s subshell. This is why it's important to remember the distinction between energy levels and subshells. All of oxygen's 6 valence electrons are found in its second energy level, the energy level that has a primary quantum number of 2. Even though these electrons are in different subshells, they are in the same energy level. An energy level is what we mean when we talk about outermost electron shell in reference to the location of valence electrons. I know this seems to go against what was stated earlier, but this is why it's important to go over electron configuration early before more confusing conflicts of terminology arise. From now on, valence electrons can be defined as the electrons located in the outermost or highest energy level of an atom, the orbitals that are furthest away from the nucleus. Electron configuration is a tricky topic, so we'll leave it there for now. In the next video, entitled Unit 1 Video 5, we will be introducing orbital diagrams. Thank you for watching.